We are continuing our work with folding the circle. We are looking at triangles and tetrahedrons for this one. So we took every other point and folded it to the center, and that gave us this triangle. You will see my illustrations here and here. Then we made observations. There were many about these triangles. All kinds of triangles are represented here, including scalene, isosceles, equilateral, and right triangles. And there were a total of 16, if we counted correctly. From here, we took each of these outside points and brought them all the way to the opposite midline. Not doing that very well, and folded them. That gave us an inscribed equilateral triangle in the center, and essentially gave us a net for a tetrahedron, which was really cool. We looked at all kinds of various things. This book is from Red Hen. It's Whole Movement, it's Folding the Circle. It's Bradford Hanson Smith. He has wonderful art sculptures. Geometric, you should take a look at that. So this is the work that we did in folding the circle and finding the net for the tetrahedron. We also looked at the viewpoints of the tetrahedron and the lines that we ended up with, making observations about this. Then we went on to talk about the different frequencies of tetrahedrons. And then we made another tetrahedron with our tetrahedrons. And we made an even larger tetrahedron over there with our tetrahedron. That was a lot of fun to make. And we talked about fractals, because that is a fractal. It is a 3D representation of Sierpinski's triangle, which I have drawn over here, and hopefully we will have time to dive into some fractals work. They're really fascinating, but there's just never enough time. Okay, so the last thing that I wanted to show you, when we were doing the Notice and Wonder for our Platonic solids, looking at faces, edges, vertices, and shapes, because there is a definite pattern here. She asked for a sheet of paper so that she could color code them, which I think is ingenious, and color coding in math is so helpful, especially in the later years when you are looking for different patterns or trying to keep up, particularly with geometry with like angles and stuff. Color coding is awesome. I'll show you that in a second, but there is a definite pattern here. You will see the symmetry here with the tetrahedron, and that basically is because the tetrahedron is its own dual, which we will go into later. The cube and the octahedron, you'll notice how they are opposites of each other. There is symmetry there as well. They're just flip-flopped in the pattern. That is also because they're a dual, and the same thing happens with the dodecahedron and icosahedron, is that they flip in pattern and they are a dual. So color coding is awesome. Do more of it. Let me show you. These are color-coded angles for picture proofs. She actually measured her angles. I did not measure my angles. And here are more color coding for picture proofs. I think I have some in my notebook. Here we go. All the equal angles are the same color. Same here, equal angles, the same color, and our picture proofs. This is basically a balance proof, saying that we know A, B, and C are equal to 180 because that's the internal angles. That proof is up here. And then we also know, because this is a straight line, that B and D are equal to 180. So if those two things are set equal against themselves, we know that they have angle B in common. If we take out the angle B, then we know angles A plus C is equivalent to angle D. So this is a picture logic proof of external angles being the sum of the two opposite internal angles.